And when I went to visit him, in Indiana, of course, a beautiful campus there, which he, part of the reason he stayed there is because of a beautiful campus surrounded by beautiful music. In fact, the first time I enjoyed opera was when Russ took me to the opera house there. And I went to visit him in his house, and I'm a little bit into carpentry. And the first thing I see is like a beautiful sofa that he designed himself right in the middle of the room. And of course, there is this beautiful book which just came out on probabilities and trees and networks, just 20 years in the making. And it's I think the most important job for us mathematicians is to create a language of science, right? And in some sense, Grothendieck says that if you create the right language, then all the proofs will be trivial, which is maybe it's of course not this whole thing is not a trivial issue. What Grothendieck didn't have is the elementary nature of the language that you should create, and what I think, and when the language that we create is infused by this beauty, then of course that makes all of our life much better and much more happy. So this is something that I really like about all of Russ's work, and thank you, Russ, for all this. So my choice of topic is going to be actually, so returning to this elementary part, as you know, Russ and others had for a long time something called the Institute for Elementary Studies. So there is also this commitment of talking about basic things. And so my choice of topic was essentially influenced by this, because I wanted to talk about really basic things. So if I talk about basic things, I better not talk about something that most people know here. So I'll have sort of an orthogonal talk, which is about random matrices. Now, random matrix talks, if you have been to them nowadays, tend to be very technical and involve a lot of list of very strong results and no proofs. So my talk is going to be completely the opposite. It's not going to be technical. It will have no new results, and it's going to have proofs. So that's the goal. And hopefully it will relate to some of the other things that we have discussed. So let's talk about. First of all, let's talk about spectral measure. Okay, so what's the setup? Let's say that you have a graph G, which is of bounded degree. So there is, let's say that we have an absolute bound on the degrees of G, and let's say that you have a vertex O in this graph. And what we want to define is the spectral measure of G at O. Right, so this is the spectral measure of the adjacency matrix. So one way of defining it is simply by saying that if you integrate the spectral measure with respect to x to the k dx, so look at the kth moment of that, then this is going to be, so let's say the adjacency matrix is A. This is going to be A to the k O, right? So this entry, which is just the number of paths of length k that go from O to O. So this, may or may not exist a measure like this, but it's a fact that, say, if it's a finite graph, this measure exists. In fact, you can write it in that case explicitly. You can write sigma GO as sum over the eigenvalues lambda of the corresponding eigenvector phi sub lambda. So this is with multiplicity evaluated at O squared. This is the weight, and then the location is, of course, the eigenvector. So you can check that. Yes? Eigenvectors of what? Eigenvectors of A. Yeah, finite graph. This is the finite case. Oh, okay, so in the finite case, you can check that this satisfies that. So it implies that measure exists. The infinite case, this still exists, and actually it's an exercise to figure out. It's easy to figure out that this thing exists. The reason this is interesting as part of it is because it's a nice geometric concept, the spectral measure in some sense, because you let's say that you have some rooted graph, so Gn O, converge to some limit in the rooted sense. So what does this mean? This means that if you look at, for any r, the r neighborhood of this vertex O eventually stabilizes to be the r neighborhood of this G, of O in G. Right? So that's what this convergence means. It's very simple. Of course, then this implies that sigma G and O converges to sigma GO weakly. Right? That's just because the moments not only converge but stabilize, because the path of length k from O to O are determined by the R neighborhood if R is less than k over 2 or greater than k over 2. So this is clear. So in fact, what you get is that this spectral measure is a continuous functional from space of graphs with respect to this rooted convergence. So let's look at an example, very simple example. Let's take Gn to be the n cycle. Okay, so the n cycle. If you look at the n cycle, you can compute its eigenvalues exactly, because the adjacency matrix just looks like. Let's take T to be this matrix. So this is the right shift, right? So you look at the right shift matrix. Then the eigenvalues of this are e to the I kn, if this is n by n, right? The eigenvalues of the inverse are also the same. And if, excuse me? K over n. The eigenvalues of the inverse are, of course, the same. And T plus T inverse is exactly the adjacency matrix of the n cycle, right? So, and of course, they commute. So the eigenvalues of T plus T inverse are exactly these guys, with a minus here, because they get inverted. Excuse me? 2 pi, okay, sorry. Yeah, 2 pi. Okay. So let's think of this geometrically, right? You have the circle, and you have these evenly spaced points. And if you make this circle to be of radius 2, then these numbers are exactly the projections of this to the real line, right? Okay. So the spectral measure, well, this actually tells us the eigenvalues. Now we also have to figure out the weights. Now, for the weights, notice the following things: that if you add all the spectral measures over the various roots, right, then these things will sum up to 1 because the eigenvectors for an orthonormal system. So you're just going to have the eigenvalue counting measure. Right? But in this case, all the spectral measures have to be the same because the graph is vertex transitive. So this actually, the spectral measure in this case is just exactly the empirical distribution of the eigenvalues. So the weights have to be all 1 over n. So what happens with this measure when we get n go to infinity? Well, it's just going to converge to the projection of the uniform measure on the circle to the real line. Okay? So this is what you get. So sigma of z, just z, which Gn, of course, converges to the integers, the integer graph. Sigma of z is equal to this projection, which is the arc sign on -2 to 2. So that's just a simple example. So let's look at another thing. So let's just go back to this fact. So that we discussed before. So if you look at the eigenvalue, empirical distribution of eigenvalues, so let's call that mu. So it's 1 over n sum of delta lambda, right? Then we know that this is the expectation, the average of those measures with respect to O, right? With respect to the choice root of sigma GO. So if you average the spectral measures with respect to random choice of root, you get the eigenvalue distribution. So you can also, so how does this appear in terms of convergence? Well, you see that this is the natural notion of convergence now. If you want these measures to understand the limit of these measures, is to take a sequence of graphs Gn and pick the root uniformly at random. Okay. So a sequence of graphs Gn converge to some random rooted graph Go. Okay. When you pick in the what's called Benjamini-Schramm strands. So this Benjamini-Schramm convergence is, I know, it's known to almost everybody in the audience. So actually, even almost everybody in the audience has a different name for it. In fact, I think Itai, who is the first one of these, he could settle for BS convergence, but. So again, you have this sequence of unrooted graph. It converges in the Benjamini-Schramm sense to a random rooted graph. If, when you pick the root uniformly at random, then you have convergence in distribution to this guy with respect to this local convergence topology. And this is just equivalent to saying that the probability of seeing a certain neighborhood when you look at distance r is converging to some limit, which is just the probability of seeing that neighborhood here in G for every such neighborhood. And what you see is that by a continuity theorem, if you have this kind of convergence, then mu n necessary, which is actually the expectation of sigma n, sigma G N O, right? This is the empirical eigenvalue distribution, is converging to the expectation of GO. Sorry, sigma GO. Right, so this is just bounded convergence theorem and the continuity theorem. These are probability measures, so there's no problem with unbounded things. So this is a Benjamini-Schramm convergence is a very nice way to understand limits of eigenvalue distributions of graphs. Okay. So let me put this aside a little bit and talk about something else. And that's the GOE. Which probably all of you know. So what's the GOE? You take a matrix M, which is just okay, so I have used my A. Just 1 second. Okay, let's say new notation. Okay, so M is just a matrix which is IID normal 0, 1. And if you take M plus M transpose over root 2, that's GOE. So we're going to call this A now. Okay, that's what it is. When trying to understand, so you may ask, what is the spectral measure of GOE? Well, that's, on the one hand, you know that the spectral measure of GOE has the eigenvalues. And what are the weights? Well, the weights, they have to be a Dirichlet distribution, which is independent of the eigenvalues. And that's just because of this O. Okay, so the O in the GOE means that it's invariant under orthogonal conjugations. And if you take an orthogonal conjugation, that will change the spectral measure, but not the eigenvalues. Okay. So from that it follows that these weights or the phi i's have to be invariant, on the sphere under this conjugation. So it has to be according to Haar measure, and then the squares are going to be then Dirichlet distributed. Okay. So how do we? What's a good way to understand the GOE? So this is an idea that's due to Trotter, 82, which is to understand it through something called tridiagonalization. And what he used this idea for is actually to prove the Wigner semicircle law. And I'm going to do that essentially giving his proof, although given in a slightly different language, which is somehow maybe a little bit more transparent than the original proof. So what's tridiagonalization? So this is something that is in the first step of so-called Lanczos algorithm, which is a way to compute the eigenvalues of a matrix, but it's also a way to store the eigenvalues of a matrix. So suppose that you have a large matrix, n by n, and you don't really want to compute the eigenvalues because those involve nasty operations, right? Solving algebraic equations, but you would still like to reduce the data, which is n squared, right, to something of order n. And that's what this tridiagonalization argument is good for. So here's how it looks like. So you start with a matrix A, which is symmetric n by n, and you get from this a matrix J, which is a Jacobi matrix. So it looks like A1, AN, B1, BN, B1, BN. And it's 0 everywhere else. So it's just a tridiagonal symmetric matrix. And the conditions is that the BIs, we would like them to be positive, but sometimes they're just non-negative, and the AIs are arbitrary. So there is a way to do this with just simple linear transformations, and here is how it goes. If you think of your matrix as follows, so let's write this matrix A, and write it in this block form. So this is the 1 by 1 block, which I call A. I call this n minus 1 by n minus block C. Let's call this B and B transpose. Okay, and let's conjugate it by something. Put here an orthogonal matrix O. Let's put it like this. You put here 0, 0, and 1. Okay, so it's a special orthogonal matrix that fixes the first coordinate vector. You conjugate it by this, so the same thing inverse. Okay, that inverse, just put it like that. So what do you get? It's actually easy to write it out explicitly. Your A doesn't change. Okay, the B gets multiplied by this O. You get, of course, keep a symmetric matrix, so it has to be OB transpose here, and then you get a C conjugated by O. Okay. So this operation, of course, is a conjugation by an orthogonal matrix. Doesn't change the eigenvalues. In fact, it does a little bit more. It doesn't change the spectral measure at that vertex. Okay, so that's easy to check. You're fixing actually this coordinate direction, so that implies that the spectral measure is fixed. And now you would like to get into this direction, right? You'd like to make this thing 0 outside this middle line. So you just pick the B. So you just pick the O, so that it rotates A into a coordinate direction, the first coordinate direction. Okay, so you're going to have OB to be equal to some vector of the kind which is the length of B. Right? You can do it. It doesn't change the length, and then afterwards it's going to be 0. Like that. Okay, so then with one step like this, you've zeroed out things in the first row and first column where they need to be 0, and then you can just continue with bigger blocks and do the same thing and get a tridiagonal matrix. Okay. So in fact, this is very direct, and but you can also direct and algorithmic, but you can also say it more theoretically. So you could say that if two matrices are equivalent, if their spectral measure at the first vertex is the same, okay, then there is a nice way of talking about equivalence classes. So if you restrict to matrices where the spectral measure is actually supported on n distinct points, this is not always the case, but it's generically true. Then then you can say that two matrices are in the same equivalence class if you can get to one to the other by a conjugation by a matrix like this. This is one thing. And the other thing is, in every equivalence class, there is a unique representative, which is a Jacobi matrix. So there is it's a kind of characterization like diagonal matrices for the equivalence of eigenvalues. Just talks about a richer equivalence. What I proved is that every matrix has a Jacobi matrix version, okay, which is conjugate to it by an orthogonal matrix of this form, and that has exactly the same spectral measure as the original matrix. I didn't prove uniqueness, but it's also true. Okay? In this class where the spectral measure is supported on endpoints. Now, Trotter said that, well, this is nice. You can actually apply this to GOE, right? And it's kind of clear that you can, because what happens, right? So you have a GOE here. Okay, if this was a GOE, then a submatrix is also going to be a GOE, right? Because that's a property of GOEs. What do you get when you do this conjugation? Well, this A is unchanged. That was a normal 0, 2 in the GOE. Just write it. Maybe I call it N1. Okay, in this step. What is this OB going to be? Well, it's just going to be the length of a normal vector in dimension n minus 1. So that's a chi n minus 1. I'm going to write it like this. Okay. And then what is this submatrix going to be? Well, it's just a GOE conjugated by an orthogonal matrix. Now, this orthogonal matrix is random, so that could be a problem. Because, of course, it's not true that GOE you conjugate by any orthogonal matrix. You could diagonalize it by an orthogonal matrix, right? But fortunately, this orthogonal matrix did not depend on this C. It only depended on the B. Okay, so if you conjugate by an independent one, that's still fine. So this is going to be a GOE, and you can continue this thing. So you get something like this, N2. Sorry? The B's don't depend on C. Yeah, that's right. They're independent. That's a nice fact. Okay, and so you get down to is you have this decreasing thing of chi's. And here you go. So that's so the theorem that we prove now is that sigma of this matrix is the same in distribution or even equal if you do this thing as sigma of GOE and sigma at O at the first coordinate vector. Yes, everything is independent. That's right. Okay. So let's prove the Wigner semicircle law because we're there now. So there are two things. So let's think of this guy. So let's look at this matrix J, and let's divide it by 1 over root n. Okay. And let's think of it as some adjacency matrix of some weighted graph. Okay. So what should you remember? So one thing that you should remember is that if you look at the chi variable with parameter n, then asymptotically this is square root of n plus a normal 0, 1/2. Okay. So that's some CLT you can prove there. That's good to know. So what does this guy look like here? Well, let's draw it. So of course the graph, because it's a tridiagonal matrix, is just a line, right? But you have weights in here. So the weight here is a chi n minus 1, and it's divided by square root of n. So chi n minus 2 minus square root of n. Chi 1 divided by square root of n. And then you have these normals, right? N1, N2. And they're all divided by square root of n. Okay. So we want to understand the limiting eigenvalue distribution of this weighted graph. So one observation, of course, is that putting weights in the graphs will still go through the previous theorem of Benjamini-Schramm convergence. You just have to assume that the weights also converge, right? Not just the graph structure, but the weights there. So what does this graph converges to in Benjamin-Isham sense? Well, let's see. So first of all, look at this thing. So the normal here is divided by a square root of n. So it's gone. Okay, in the limit, you don't see a normal. You just have all you see is z with some weights. Right? Of course, the random root is going to be somewhere far away from the boundary. So what you see is z. You will not see that this is finite. So graph structure is going to be z. And they're not going to be loops. The other thing you don't see is this normal, because that will also get scaled out. So in fact, this doesn't matter. Okay, the randomness in this graph, the randomness in GOE, doesn't matter in terms of this limit at all. Okay? So those will get scaled out. The only thing that will matter is this square root of n. What are we doing? We're looking at the random location, square root of k, which is chosen from 0 to n, or 1 to n uniformly, and you divide by square root of n. So what is this? What is the Benjamin-Isham limit? Well, it's just a weighted graph. So let's put the weight here r. And one observation is that all these r's are the same. Okay, they're not independent. They're exactly the same r, because locally the weights change very little. The other observation is that r is going to be, well, it's going to be a square root of a uniform, right? Because you take square root of n. So I could write it like this. So the probability that r is less than or equal to regular r is r squared for r in 0, 1. Okay. So this is the Benjamin-Isham limit. So we have this limit of your graph. Now let's look at what is the limit of the eigenvalue distribution. Well, it's just, we know what it is, right? It's just the expected spectral measure of this graph. Now, where is the expectation? So the only thing where the expectation comes in is that this r is random. Okay? And what's happening here? Well, if I fix r, I just get the projection of the eigenvalues of the circle of radius 2r onto the real line. Okay? But if I pick r at random according to this measure, then I get the projection of a random circle. But what is the distribution of this circle? What is the joint distribution together? Well, it's the same as if I just pick a random point from the disk of radius 2r and project it down to the real line. Because the random point, the radius, satisfies this. Okay, so basically you get that this is it, and this is the Wigner semicircle. So we have a proof with no computation of the Wigner semicircle. So let me give you another proof of the Wigner semicircle law with no computation. Let's look at this graph again. Okay? And now let's look at it in terms of rooted convergence. So we put the root here, and let n go to infinity. What do we get? Well, we get, just by the argument before, we get the graph now rooted here. So it's going to be z plus with this ends here. And the spectral measures, sigma on, converge to sigma of z plus o. Okay? So this is a spectral measure. It's not the eigenvalue distribution, because we didn't pick a random root. We picked the fixed root. On the other hand, if you go back to the original model, the GOE, there is nothing special about this vertex. So it tells you that the spectral measures at all vertices have to converge to this thing. So their average has to do the same thing. Okay? So mu n has to go there as well. It's just the average of things like that. This is deterministic. This is convergence in probability, by the way. Just like there. So that means that this spectral measure, is again the same as the Wigner semicircle law. Okay? So there are two things you could do with this proof. You could say, well, we already proved it. And then we could deduce something about the Wigner semicircle law, because we know that these two things have to be the same. So let's do that. What can you deduce? Well, what you can deduce is the moments of the Wigner semicircle law. Because what are the moments? They're just the number of paths in Z plus from O to O that stay above 0. So they're exactly the Dicke paths. Like it like this, right? So MK is the number of Dicke paths. Or if you just want to use this proof by itself, then you can just say, well, things with moments given by the Dicke paths have to be the Wigner semicircle law and deduce it some other way. Okay. So I have given proof of Wigner semicircle law. Let me give you another theorem, which is Komlós-Füredi. So which asks for the following thing. So you know this rescaled eigenvalue distribution is converging to the semicircle, but you may be interested in what is the top eigenvalue. Okay? So what is the lambda 1? So this is lambda 1 of, let's say, J over root 10. Lambda 1 converge to. Right? So it's natural to conjecture that this converges to the top of the Wigner semicircle law, the top eigenvalue, which is 2. Okay. But from the weak convergence result, the only thing that you can deduce is that it cannot converge to anywhere below. Right? Because there is mass of eigenvalues below it. But since it's weak convergence, this thing just has weight 1 over n. You don't really see it in the limit. So it could go to infinity as far as we know. So how do you proving this in the classical world involves just more sophisticated path counting arguments than here. But actually from this model, it's very simple. And it follows right away from a lemma. So let me give you the lemma. And I'll prove the lemma. Okay, so the lemma tells you that lambda 1 of J, of a Jacobi matrix, is less than or equal to the max over I of AI plus BI minus 1. Okay. Where we say the I's and BI's were the things on and off diagonal, and we have to set B0 equals Bn, because those don't exist, they have to set them to be 0. Okay. So this is a lemma. Let's prove it. Okay, so it has a one-line proof. Let's introduce the following matrix. I'm going to put zeros in the first row, and in the second row I'm going to put square root of b1, and here minus square root of b1. Yes, so that's one way. So you use the Greshgorian circle theorem. It's another way to do it, right? So it's supported by the maximum. It's greater than the maximal absolute row sum. Yeah. Let me see. Now you're confusing me. AI is not non-negative. There can be positive, yeah. No, but it can be negative. Can be negative. That's right. Yes, but it's still true, like this. Okay, so let me give you this proof. Okay? Let's see if I got this right. So b1 minus b1 b2 square root of b2 minus square root of b2 square root of b3 minus square root of b3 and so on. Okay, so you see this matrix. Let's call this matrix, I don't know, b. Okay, and then the b's are positive. The a's are not. Wait. Let me finish. Let me finish. Okay, so we're going to write J. It's the following thing. So I'm going to look at minus B transpose B. Okay, so B transpose B is going to give the inner product of the rows, of the columns of B in the entries of the matrix. Okay, so it's going to be it's actually done in a way that on the off diagonals you get exactly the right things. Right? So it's going to be a tridiagonal matrix because this is bidiagonal. It has exactly the right things on the off diagonals. So all you have to do is fix the diagonals. Okay, so what do? You add to it a diagonal matrix. And what do you have to put in there? Well, the AIs have to be there. And if you check what are the on the diagonals here, you get the length of these vectors. Right? So you get actually AI plus BI minus 1. Okay. And so the top eigenvalue of this matrix is less than or equal to the top eigenvalue of this matrix, but this is a non-positive matrix, so it's 0, plus the top eigenvalue of this matrix, which is diagonal, which is equal to that. So it's one line. And let's do... So what is this thing, right? What is this thing in our case, right? So it's max over I of what do we have? So you have here a normal, Ni, right? Plus you have chi I plus chi I minus 1.
So it says B transpose B plus this 2, and then B is singular?
So this matrix, for any matrix, if you form this, it's going to be positive, non-negative definite. So this is non-positive definite. So the top eigenvalue of this is 0. And the top eigenvalue is sub-additive in this way. So we just use that. Okay. And so what is this? Well, what is this max I? Well, this has Gaussian tails. So there are n of them. So, the most of this is roughly root log n. Okay. These guys also have Gaussian tails. Okay. So what you get is 2 root n plus root log n times some constant, random constant c. Or you can have it a fixed constant, and this holds with probability tending to 1 with n. Okay, and so this tells you that the lambda 1 is actually sticking to the boundary, and it actually gives you a fairly good rate of how it sticks. If you want to get this rate with path counting, you have to do a lot of work. Okay. So let me tell you, so we have proved convolution theory, and let me tell you something which is slightly newer, and that's called the BBP transition. Okay, so BBP stands for Baig-Benarus-Peché, and it's actually the thing in random matrix theory that is most used everywhere in the world now. I think it's in undergraduate engineering textbooks now. So what it is about is the following. If you have some normalized data matrix, then you can understand the structure of the matrix by looking at the top eigenvector. And how much structure there is measured by how large top eigenvector of the covariance matrix of this data. And you can understand how much structure is there by looking at how large this top eigenvector is, or how large the top eigenvalue is. Of course, you have to compare it to the case when there is just noise and no correlation. So that's the null case, because then, of course, you see fake correlations just coming off the noise. But then you want to see, well, when can you tell? If there are correlations, can you tell them? Okay. And the answer to that is something very strange is happening. If you introduce just, say, a single correlation, I won't tell you what it is, then for a while you don't see it, and then suddenly there is a phase transition when you start seeing it.
As the noise changes?
As the strength of the correlation changes, yeah. So you basically you can translate everything to diagonal matrices because of invariance, because the only thing that matters there is the covariance matrix, the population covariance matrix. If you have a Gaussian model, and if you have one, the null case is when all the diagonals are 1, and this BBP case is when there are just a few things that are not 1. So the simplest case when there is only one thing that's not 1. Okay. So that's what roughly the BBT transition is, but I don't want to say it precisely because I'm getting out of time. There's a version of this for GOE. Okay, so GOE version. probably I won't prove it, but I'll tell you the hint of the proof. So the GOE version looks like this. If you look at the lambda 1, if you put 1 over root n of lambda 1 of GOE, but now you add to it not to some mean. So you're just going to look at the top eigenvalue of GOE with non-trivial mean. Okay, so let me put it like this. So you take the matrix 1, 1 transpose, which is the all 1 matrix. Okay, so this would make this guy's mean 1. Okay. But the right scaling is you put a over root n here. Okay. And the GOE version of the... So this is going to be... the entries are going to be normals with a tiny mean change. Okay? 1 over root n. And these are standard normals. They're not normalized with n. The theorem tells you that this thing converges to something we call, which is phi of a. This is in probability, as n goes to infinity. And phi of a is this BBP transition function. And what does it look like? So phi of a is equal to 2 if a is less than or equal to 1, and equal to a plus 1 over a if a is greater than or equal to 1. So what you see is that adding this mean, if the a is less than 1, doesn't change the behavior of the top eigenvalue. But if it's even a little bit above 1, it does change. And there is a discontinuity in the third derivative or something. Okay, and so this is the BBP transition function. And let me, instead of proving this, let me give you BBP a lemma, which is important in the proof. And you may be able to figure out the proof based on the lemma. So let's say it's BBP for Z plus. Okay? So what's BBP for Z plus? So you take the adjacency matrix of Z plus as before. You get the top eigenvalue. Now, top eigenvalue, of course, this is an infinite operator, so there aren't necessarily eigenvalues, but the top of the spectrum you can define by Rayleigh quotients, right? The sup over. So I'm looking at this graph, which is 1s, and put here a loop with A. Okay, so this is now just a single number, and the statement is that this is equal to phi of A. Again. So already if you just do it in this case, you get phi of A. And how do you relate these two things? Well, of course, do the tridiagonalization, make this perturbation into the first coordinate, and then you look at the local convergence that you're going to this graph. And then from the local convergence, you can deduce this BBP transition. So, okay, I'll stop now and let room for questions. Thanks.